All right, so good morning again. So as usual, I wasn't able to monitor the time, so that is why it forcefully closed our meeting. So I apologize for that one, for improper, uh, closing. Or disconnection of our meeting. Anyway, so let me just check if you guys are already in front of your computers. So just give me a thumbs up. All right, so great. Most of you are already here. So there were two who didn't respond. Anyway, all right, so moving on to example number 6. So still have the same example, but this time we now have a non-ideal diode. So in here we have positive to negative, negative to positive, so negative to positive, positive to negative. So all throughout, even though we have this, connections with the voltage with our diode, so it's still a reverse bias all throughout. So as a result, our reading in VO is 0 volts. Okay. So I hope we're clear with this one. And then during the negative half cycle, so still the same. It's just that we now have a value on our voltage threshold, which is 0 0.7. So before it's just exactly negative 3 volts because our voltage threshold is 0. But in here, we now have 0 0.7. So from negative 3, it became negative 2.3. Okay, so just apply KVL, okay, in this circuit. So are we clear on how did we get those values?
Clear po, sir.
Okay, great. So again, if ever you have a question, so just let me know. Okay. And let's now move on to a series negative clipper. So whatever you got, you guys have learned from slide 1 to slide 22, just reverse that one. Okay, because in this following slide, it just simply clips the negative side instead of the positive side. So that is why it's called series negative clipper. Okay, so we have a reading in positive cycle, but in the negative half cycle, it was completely clipped. Okay, so yeah, and these are the things that you can use or you can defer to upon computing the voltage output on the positive half cycle. Okay, VI minus VD, and then during the negative half cycle, so of course, all throughout this one is 0 volts. Okay, so without a further ado, let's start with example number 7 on the series negative clipper. So again, as usual, we'll start with ideal diode first. So just check the connection, positive to positive, negative to negative. So we have here a complete forward bias connection. So as a result, we have a 5 volts reading on this path right here. Okay, so I hope this one is clear. And the reason why this one is 5 minus 0, because again, this one is ideal. So hope super simple. All right. Oops. Yeah. And during the negative half cycle, so again, just check the connectivities. So we have negative to positive and then positive to negative. So all throughout this one is a reverse bias. So as a result, we don't have a flow of current, okay, on this circuit. So that is why we have 0 volts reading on this path right here, or in this voltage output right here. Okay. So I hope we're clear with this one. And of course, after this ideal diode, we now have a non-ideal. Okay, so just deduct that voltage threshold. So 5 minus 0 0.7, we have 4.3 volts on the positive or during the positive half cycle. So I hope we're clear. Are we good so far?
Yes, sir. Kukuha naman po.
Okay, great. And then during the negative half cycles, as usual, even though this one now is a silicon diode, so that one still a reverse bias connection. So all throughout, we don't have a flow of current on this entire circuit. So that is why we have 0 volts reading on this VO right here. Okay. And then let's now move on to a series negative cleaver with bias connection. So in here, we now have, again, the positive bias and then the negative bias. Okay, so again, this one is just simply explaining the connectivities, etc., etc. But I highlighted this one because you guys have to take note that the value of our voltage output, again as usual, depends on the value of our VB and VI. So clipping take place during the negative cycle only when the input voltage is voltage input is greater than bias voltage. So it is saying that we have the complete uh, uh, let's say clip negative part if we have a higher VI than VB. But if we have a higher VP, then that is not the case anymore. Okay. So again, here are the formulas that you can use during the positive half cycle and then during the negative half cycle. So I think it's the same with what we have in here. But yeah, as usual, just like what I advised you guys a while ago in a series positive clipper, do not heavily rely on this formula. So just rely on your analysis. Like you can just simply apply KVL right here, and then whatever you will get, that's the reading of your VO. Okay, and same with the negative half cycle, because sometimes this 0 volts right here has a reading, especially because of the bias voltage or the voltage threshold. Okay. Anyway, so let's start with example number 9 for this bias voltage on the negative clipper. So let's start with the ideal diode first, of course. So we have here during the positive half cycle, so positive is connected to the positive and the negative is connected to the negative. So it has a forward bias connection on this voltage input right here. But on the other side, we have positive to negative, negative to positive. So all throughout, on the right side, we have here a reverse bias connection. So the one that will dictate the flow of current is the VI only, since that is the only one that has a flow of current in this diode right here. So just simply apply KVL. Okay, so counterclockwise flow of current is a no-no already because this one is a reverse bias connection. Okay, so you cannot compare that, VI is greater than VB, etc., because there's nothing to compare. Okay, because at first there is no flow of current on this side. Okay, due to these connections. But for the clockwise connection, we do have a flow of current since we have positive to positive and then negative to negative. So this one is a forward bias connection. So just apply KVL and then you will get the voltage reading on this path right here. So we have positive 5 and then this one is ideal. So this one is 0 and then we have here negative 2. So positive 5 minus 2 is equal to positive 3 volts. So did you guys get that one? Oh, hello.
Yes, sir.
Just let me know if you guys are confused and why is it 3 volts. Okay. And during the negative half cycle, so again, just analyze the polarities of your voltages. So we have negative to positive, positive to negative, positive to negative, negative to positive. So all throughout, this one is a reverse bias connection. So that is why we have 0 volts reading on this VO right here. Okay. So don't get confused on this one. Okay. So sir, we do have a reading on VO. So as you can see, sir, we have 2 volts right here, and then it will flow on this one, etc., etc. So no, okay, that is not the case because as you guys can see, we have an open circuit right here, and then if we have an open circuit, even though there is a voltage that is flowing here, so that is not a complete loop. So we should have a positive side and then a ground connection. So in here, it's like a positive side only, but we don't, there is no connection in ground because it was cut on this certain path right here. So that is why it's 0 volts reading, not 2 volts or not negative 2 volts. Okay. So are we clear with that one? All right. So let's now move on to the non-ideal. Okay. So same everything. So just add the voltage threshold of your diode. So 5 minus 0.7 minus 2 is equal to 2.3 volts. Okay, so from 3 volts, of course, this will become 2.3 due to this silicon diode consumption of a certain amount of voltage. So are we clear?
Yes, sir.
Okay, very good. And during the negative half cycles, as usual, everything is reverse bias, even though this one has a value of a 0.7. Okay, so this connection right here is reverse bias, and then this connection right here is also reverse bias. All throughout, we have an open circuit on this diode. So it's a 0 volts reading. Okay, and then let's now move on to a series negative clipper with negative bias this time. So in a negative bias or series negative clipper with negative bias, we now have a reading in VO, I mean positive half cycle of VO, and then we now also have a reading on a negative half cycle VO. So for the positive half cycle, so you just have to consider everything. Okay, VI minus VD plus VB. But for the negative half cycle, you only need to consider two. Okay, so that is the bias voltage and then the voltage threshold. So again, instead of heavily relying on this formulas right here, so just analyze the circuit itself. So nevertheless, if it's a series negative clipper, series positive clipper, positive bias, negative bias, okay, just don't memorize those formulas. Just just simply apply Ohm's law or KVL, okay, on that certain circuit, and then with that, you'll be able to get the BO without a problem. Okay, just simply apply what you guys have learned in circuits 1. Anyway, let's have this example number 11. So this one is a series negative clipper with positive bias. But let's start with ideal uh, diode first. Okay, so just check the polarities of your voltages. So positive to positive, negative to negative, negative to negative, positive to positive. So all throughout, this is a complete forward bias connection. But then again, there is only one flow of current that will dictate the current or the flow of current of your entire circuit. So it could be the V1 or the V2. But as you guys can see, whichever is the higher voltage, that is the one that will dictate the entire flow of a current on the circuit. So we have a clockwise connection. So after that, just apply KVL. So we have positive 5 right here, and then this one is ideal, so this one is 0. And then we have positive 2 right here. So plus 5 plus 2 is equal to 7 volts reading on this VO right here. Okay, so that's how we've got this 7 volts right here. So hope we're clear with this one. All right, so just let me know if ever that you have a question. And then during the negative half cycle, so as you guys can see, we now have a value of negative 2 volts. So how did we get that one? So let me just copy this one. Okay, so just check again the polarities of your voltages. So we have negative to positive, positive to negative. So on the side, okay, on the side, we have here a reverse bias connection. Okay, so it won't affect now the value of our VO of this V1 stone since we have a reverse bias connection on this left side. But on the right side, this diode and then this bias voltage right here, we have here a negative to negative and then positive to positive. So as a result, we have this flow of current right here, okay, wherein it will make this diode a forward bias. Okay, So how do we read the value of VO again in here? So again, this one is a DC voltage. So this is a constant 2 volts. But on this one is a AC voltage. Okay. So of course, this will start with -1, and then let's see -2 and then -3 until it reaches the maximum voltage, which is -5. Okay, so during the 0 volts, or let's say 1 volt, -1 volt reading, okay, so it's already or there is already a current that is passing through this diode right here, which is this bias voltage. So -2 volts will pass through this one and will pass through this one, and then we now have a complete loop of current of this V2 right here. So since this one is ideal, so of course we now have here a reading of -2 volts during the let's say V1 AC V1, which is let's say -1. Okay, until it reaches before the uh, 2 volts. Okay, because once this one became say -2 volts, then or let's say -2.1 or higher than +2 volts, it will now stop the flow of current since this one now is completely reverse bias, okay, due to this voltage input right here. So as a result, we now have an open circuit at the time, and then that is when our voltage input is greater now than our VB. So that is -2.1 up to -5. So at that certain time, it's completely reverse bias connection. So as a result, we now only have here a reading of uh, -2 volts. And then again, we now have another reading for the positive, and then the same that will happen again on the negative up cycle. So are we clear on how did we get this -2 volts right here? So if you need more explanation, yeah, maybe we can do that one. So maybe I'll just speak in Tagalog for easier way of explaining things. Okay. Well, yeah, that's hello. Meron bang nagsalita? Anyway, so yeah, that's how we've got the value of -2 volts. Okay. So let's now move on to example number 12. So we have here same example, but this one is non-ideal. Okay. So in here we have a connection of positive to positive, negative to negative, negative to negative, and then positive to positive. So as a result, all throughout this one is a forward bias connection. So again, there is only one that will dictate the flow of current. So that is the V1 since that is the higher voltage. So we have here a clockwise flow of current. So +5 minus 0.7 plus 2 is equal to 6.3 volts. So from 7 volts it became positive 6.3. That is due to this silicon diode. So are we clear? Were you guys able to follow or get this 6.3 volts? All right, so very good then. So again, just let me know if ever you have a question, okay? And then during the negative half cycle, so same explanation, just like what we have in here. So during the VI wherein it's lesser than VB, we have a flow of current which is this -2 volts. But since we are now talking about the silicon, the non-ideal, which is not the silicon diode, so we have to deduct that one. So plus 0.7 volts is equal to -1.3 volts. Okay, so that's how we've got this value right here, -1.3. So clear? I think after this is another topic again. Are we clear with negative half cycle?
Clear po, sir.
Okay, so just in case again that you have a question, so don't be shy to ask. Okay, so we now have here a new topic, which is the shunt or parallel passive prepare. So just a fact. So this word shunt is equal to this word parallel. So this is just another terminologies to the name parallel. So we could say shunt positive clipper or parallel positive clipper. So they are just the same. So in here, just the diode was placed into here. So before in series it was here, but uh, in a parallel passive clipper or parallel clipper, so the diode now is on this side. Okay, so that's the only thing that has changed. And in here, it's very straightforward. So in here, you can heavily rely on this facts right here regarding with a shunt clipper. So this one provides an output if the diode is in a reverse bias. So take note, you have a reading if it's in a reverse bias, but there is no reading if uh, this one is in a forward bias. So it's like the opposite, okay, of what you guys have learned in a previous discussion. So if it's forward bias, so there is a reading, okay. But if it's reverse bias, there is no reading. But it's the opposite in a parallel passive clipper. So you're only going to have a reading if we have a connection of a reverse bias, and then there is no reading if we have a forward bias connection. Okay. So anyway, so let's start with example number 13. So we have here a parallel positive clipper. So let's start with ideal diode first. So again, positive to positive, negative to negative. So as a result, going back right here, we have a forward bias connection. So there is no output. So as a result, we have 0 volts reading right here. Okay, so how did that happen? Well, let me just explain this one real quick. Okay, so of course we have a complete flow of current, okay, on this circuit. However, if you guys are going to take a look at this one, this VO is equal to voltage across or the voltage drop. Okay, voltage drop. And as you guys can see, there is no reading of voltage drop in here. So, since there is no resistor on this path right here. Okay, so even though there is a flow of current, which is, let's say, 5 volts, okay, but we cannot read anything since there is no load resistance need. There is no RL, okay, or there is no resistance. Where is our resistance? It's on the side. So if you want to have a reading of 5 volts, then you have to read the VO on the side, okay, not on the side. So the same with this part. So this VO right here is 0 volts. This VO right here is equal to 0 volts. But in here, we have a voltage drop key on the R1, which is now, of course, or a voltage reading key or voltage across. So they are just the same, okay, which is equal to 5 volts. So that is why during the forward bias connection, we have here a reading of a 0 volts on this VO. Okay, so are we clear with that one so far? So going back right here, that is why we have a reading of VO right here. That is because of this R1 right here. Okay, so we are reading voltage across on this entire path. And we have a reading because of this RL or this resistance right here. Okay, so I hope we're clear with this one and why we have a reading of 0 volts during the parallel connection. So are we clear? Are you guys able to get this one?
Yes, sir.
Okay. All right, and then during the negative half cycle, so as you guys can see, we have here negative to positive, positive to negative, And as a result, this one is a reverse bias connection. And then going back to our, this is like actually the formula that you can use. So it provides output during the reverse bias. Okay. So how did that happen? That is because So that is because on this point or at this certain part, we have here a like an open circuit, right? An open circuit. And then our probe is connected on this, let's say, wire right here. And then our probe, another probe is connected on this part right here. And then as a result, our 5 volts, positive 5 volts will flow on our VOM, okay, whatever is that machine that can read the current and then the voltage reading, okay, and then it is connected to our negative side. So that is why it's reading a positive 5 volts because this one served as a RL itself, or the load resistance, okay, wherein it will read a certain amount of voltage, okay. So you could just simply say that, during the reverse bias, all of our voltages will flow on this VOV path right here, or this VOM right here. So that is why we have a reading of positive 5 volts. Okay, but yeah, my bad. But since this one is a negative half cycle, so just interchange those two, and this one will become negative 5. So negative, positive. So we have here negative 5, and this one is negative, not positive. Okay. So are we clear on how did we get this negative 5 volts reading? All right. So yeah, that's the explanation behind this, reverse bias connection provides an output, and then forward bias connection, and there is no output. So it is completely depends on, on the placement of your VO also. So if the VO is right here, so you have to analyze as one. You have to think if there is reading or no. So if the VO is right here and below, then the same. Okay, you have to analyze first if there is a reading or no, etc., etc. All right, let's now move on to the example number 14, which is now, of course, non-ideal. So in here, everything is the same. It's just that we have to consider the voltage threshold. So positive to positive, negative to negative. So as a result, we have there should be no output in this one, okay? Because this V1 will just pass through here and then we'll go back right here. But since the reading or the one that we are reading is from this point up to this point or this complete path right here, so we actually have a reading, okay? And that is a voltage that consumes by this silicon diode. Okay, so this one consumes 0.7, so that is why we have a reading of 0.7 volts. Okay, so are we clear with this one?
Yes, sir.
Okay, now I have a question. What is the reading of my VO if I have a voltage input of 0.6 volts? Anyone? What is the reading of my VO?
0.6.
0.6. So what is my reading of my VO if this one is 0.6 volts? How about the others? Do you guys have the same answer, which is equal to 0.6 volts? Came from Mr. Awas.
So hindi ba same pa rin?
So anong the same pa rin? Still 0.7?
Hindi ba, sir?
Hindi ah. how will you get that 0.7 if this silicon diode wasn't able to eat 0.7 volts? So initially, it won't be able to eat 0.7 volts, or it won't be able to consume 0.7 volts because we have a lacking of voltage here. So you could say that we have a reading of 0.6 because that is the only voltage that was able to eat from our voltage input. Or you could just simply see that this one, yeah, even though we have positive to positive and then negative to negative, this one will become a reverse bias. Okay, that is because this one will, there is no enough voltage to make this one a forward bias connection. So as that result, so we can just simply remove this one, and we have here a 0.6 volts reading on this R1, and then it will pass through this VOM right here, or the VO. So still, we have the same reading, which is 0.6 volts. So the answer of Mr. Awas is correct. So yeah. Okay, that explains why we now only have a reading of 0.6 volts. So that doesn't mean that if we have here a silicon diode, so we already have a value of 0.7 volts in here. So that one still depends on the value of our V1. Okay, so if the value of V1 is enough, then this one is a constant value of 0.7 volts. But if the V1 is less than our voltage threshold, then that VI is now equal to your VO. Okay, which is 0.6 or 0.5 or 0.4 or even 0.1. All right, so time check, we now only have 5 minutes left, so I think we can still finish 2 more examples. Anyway, during the negative half cycle, we have negative to positive, positive to negative. So as a result, this one is a reverse bias connection. So our only reading of voltage is this -5. Okay, because this will become an open circuit. Okay, and then all of our voltages will pass through to our VO. Okay, there is a question. Sir, paano po kapag may bulk resistance still same po ba? No, of course. So, of course, you now have to deduct, okay, you have to deduct the value of this R1. You have to deduct the value of, let's see, if there is another voltage source right here. So, you have to deduct the value of that bulk resistance. Okay, so, yeah. So, in here, we're just considering ideal and then non-ideal. So actually, we're just doing the first approximation and then the second approximation. So the third approximation will serve as your quizzes or your exams. So yun na yung hint nyo. Okay, so make sure to practice some circuits or clippers that has a bulk resistance or a different placement of a diode. Okay. It's just that we don't have example for bulk resistance right here, but all you need to do is deduct the voltage drop on that bulk resistance. Okay. Anyway, so going back to our example number 14, negative half cycle. So were you guys able to get this one? All right. So let's now move on to, okay. So how many minutes left? 3 minutes. I guess we can explain this one real quick. Anyway, so in here we now have a bias connection. Okay, this one is still a positive or parallel positive clipper, but this time it has now a bias voltage. So of course we have here a positive bias and then negative bias. So this is what will happen if we have here a positive bias. Okay, and then this is what will happen if we have here a negative bias. And again, this one depends on the value of our VI and then the voltage bias or the VB. So for the positive
Switch
bias,
ito. Ano switch mo? Dati na ba na-call mo?
yes, Mr. Francis. Oh. All right, so going back to our discussion, so we have here the formula for the positive bias, okay, during the positive half cycle. So VD plus PB, okay. So as you guys can see, it's very straightforward. Due to this polarity, we have an additional voltage, which is plus VB. But during this negative bias, so we now have a different polarity, of course. It's no negative bias. So we now have a deduction of voltage, which is negative VB. So that is the only difference between those positive bias and then negative bias. And then during the negative up cycle, we have here a reading of voltage input. So whatever is our VI is equal to our VO during the negative up cycle. Okay. So anyway, again, don't heavily rely on this circumstances or these formulas right here. So just apply KVL, just apply Ohm's law, whatever you guys have learned on the circuits one, that's already enough. Okay. So let's have this example. So 1 minute and 22 seconds. So we have here ideal, okay, connection. So positive to positive, negative to negative, and then positive to negative, and then negative to positive. So all throughout, we have a forward bias connection. Okay, that is because of this V1 right here. So this will not affect this one since this is in a reverse bias connection. So as a result, we have here a supposedly, okay, supposedly there is no reading since this one is forward bias. Then again, we have now here a bias voltage. So we now only read the voltages, okay, on this certain path. So that is the VB. So we have here a reading of positive 2 volts since this one is ideal ending. So 0 plus 2 is equal to 2 volts. Okay, so are we clear with this one? And one more thing, again, do not heavily rely on this one because just in case that this one now is non-ideal, then yeah, if VI is greater than VB, VO is equal to VB, which is correct. But if we now